If you want to get to a specific topic, because this is going to be long, here is the topic covered with an approximate timestamp. Feel free to fast forward to that point. I do not allow for ads within my videos because I think it's obnoxious, so you can just fast forward to where you need to go. Hello everybody, welcome to the Geo-Files. This is going to be the last episode of 2020. We're going to talk about radioactive decay, and I am going to explain to you, well, the basics, because I have to. And then I'm going to explain to you why parent elements, because this came up in an online discussion, and there's a disconnect between people who think radiometric dating is BS because they don't understand it, basically, and what's actually going on. And it is hard to find some of this stuff. Like, you can go on anywhere, and I'm going to show you this, Halflifes. You can go anywhere to find that stuff, but what they don't tell you is why a parent element decays within a rock to a daughter, and it gives you the age of the rock and not say the age of the mantle that it was derived from. I'm talking about igneous, right? Because I'm going to get into uranium lead. I know creationists love carbon, and they often use terms from organic processes in carbon-14 decay to describe other radiometric dating, and you can't do that. But anyway, why does it give us the age of the rock and not the age of the mantle or the age of the supernova that created, in the case of uranium lead dating, uranium? And I'm going to get into that because I know creationists focus on carbon-14, but there's over 20 different radiometric dating things you can date radiometrically. Now, the basic principle is a half-life principle. That is all the same. Okay, that doesn't change. The only things that really change in the laws of physics are the amount of time it takes a parent to decay into a daughter. And a parent element, in which I'm going to show you here, is that original radioactive element. It's the amount of original radioactive stuff that's going to decay into something else. And it doesn't matter what kind of, if it gives off alpha particles, beta particles, it doesn't matter what it gives off radioactively. It's going to decay into something else, and it's going to follow this half-life principle regardless of what element it is. Time is going to be your biggest factor in the decay of a parent to a daughter element. And this varies wildly from a few seconds to billions of years, okay? The laws of physics and the natural world is not bound to our concepts of logic and reason. Those have nothing to do with how the physical universe works. Anybody who's ever studied relativity or even is aware of quantum mechanics in any other than just hearing about it is going to know this stuff does not follow our rules of logic. Our rules of logic are for us. And in everyday talking and arguing, they work okay. But when you start talking about the physical world, it is not bound by any of our concepts or our thinking processes. So that's an important thing to remember. That's why arguments in science don't mean anything. They're starting points and that's it. What we can observe and predict is what matters. So anyway, time. So you're going to have your parent element, which is going to decay into a daughter element in a certain amount of time, which is our half-life, which we are going to write as half there. So how does this concept essentially work? I said I wasn't going to do any equations. I'm going to derive one for you during this. Just one. That's it. Okay? I promise. But I need to show you the concept of a half-life first, and that's where the equation's going to be. All right, so we'll say we have our parent element. Doesn't matter what it is, carbon, uranium, thorium, potassium, argon, it's irrelevant. It's radioactive, it's going to decay. In a certain amount of time, half of it's going to decay into something else. So it'll decay into this. Now the decay is going to happen throughout evenly, but I cannot demonstrate that for you on a dry erase board. So I'm going to cut it into pie pieces for you. Okay, so we have our radioactive decay. We have our parent. Okay, so we start out with our parent. This is all P. After a certain amount of time, we'll say in this case, hypothetically, 1,000 years. Okay, so after 1,000 years, half of that is going to decay into our daughter. After 2,000 years, so 2 half-lives later, half more of the parent is going to decay. So we'll have 1/4 of our original after 2 half-lives. So first we have 1/2 decaying into a half, and we have 1/4 left of our parent. okay? Because it's half of a half. That's what we're doing. We're taking half of a half of a half of a half of a half. All right, and we're going to drive a quick equation for you to show you how it works. And then your third half-life, you're going to have 1/8, and I think this is as far as I'll carry it. So that's after 1,000 years, 2,000, so this is after 3,000 years. In our 1,000-year thing, we have 1/8 of our parent left. And this will continue on. Theoretically, this is going to happen forever, theoretically, but eventually you will run out of material. So that's the basic concept. Is there a way we can describe this mathematically? So, okay, I'm going to show you, and you can play with these if you want to have fun. I'm going to show you a very basically derived equation where if you're solving for the daughter, this is going to work. There are exponents involved. As you can tell, you're halving of a half of a half of a half of a half. That's an exponential relationship. So we're going to have an exponent, all right? But, so we start out, we're trying to always find our daughter, okay? So we're going to use the same symbols I used here. We're trying to find our D. So that's going to equal something, okay? Well, we know our parent is what we're working with. So it's going to be on this side of the equation because we want to eventually know how much daughter is left, okay? So we're going to have our parent, all right? And we know that there's a half-life involved. So I'm not, half of it. So we're halving things. I'm not going to write 1/2 because it might look wonky. I am going to use the decimal of 1/2, which is 0.5. So in order for your parent to become a daughter, you need to half it or multiply it by 0.5. You could also divide by 2, but we're going to stick with this because we are going to have exponents involved. Okay, so now what's left? Well, we know that in order to decay, it's going to take a certain amount of time for that element to decay. So if we're dealing with time, so if we want to know how much daughter element is left, say after a weird number like 2,570 years, something that's not an even 1,000, we're going to need our time, okay? We're going to have to divide our time by our half-life. And I'm writing half here, a common thing in case you don't know in maths, and I'm deriving this, there are more complex equations, but if you don't understand, like this is a subscript, we'll use that a lot. It's not an actual thing you can solve for, all right? A lot of times you might see something like, I've done this before when talking about density, I'll do my change in volume or something like that, my delta V or something. That's just a subscript to let you know it's related to this, but different. There's something going on there. Okay, so in order for me to get a daughter element, I have to multiply my parent by a half, but there's a time factor involved here. So whatever amount of years I want to find for, I have to divide by my half-life. In this case, it's going to be 1,000 years. Okay, but where does this go? Well, remember I said this is exponential? Just bear with me here. It goes up here. I'm not going to spend too much time explaining this and why it's up here. I will post the actual equation here and what's generally used. These symbols are not used. This is just to show you and keep it simple. All right, I've cleaned this up for you. I'm going to walk through a quick example. So we're using our 1,000 years half-life. Let's see if this works. We're just going to do a quick couple. Okay, we'll use 1 half-life. We're going to say our parent is equal to 80 grams. It doesn't matter what the unit is. I'm going to drop it. It could be 80 milligrams. It could be 80 kilograms. It doesn't matter, okay? It could be 80 pounds, whatever. 80, because it's easy to calculate this with. So we don't know our D, but we're going to plug in. So if I have 80 grams of something, and I want to know after 1 half-life, so after 1,000 years, how much is going to be left, okay? So I divide 1,000 into 1,000 by 1 half-life. This is going to divide itself out and turn into a 1 and become irrelevant. So that's going to go away in this case. So that becomes a 1, and anything taken to the first power is that anything. So we multiply 80 by a half, and we get 40. So it works, at least for 1 half-life. Let's try 2 real quick. So after my second half-life is going to be a time of 2,000 years, okay? So I'm going to have 2,000 up here, and 1,000. I'm always going to have 1,000 in this part of the exponent. This is an exponent, okay? I'm trying to not write it too sloppily. You know, because this time we're going to have 2 divided by 1, which is essentially the same as taking 0.5 to the second power, which is going to make this 0.25, because you always work your exponents first. So now we're multiplying 80 by 0.25, and we get 20. So this equation works. It's a quick little thing to demonstrate half-life, and I'm going to use an odd number here, and then we're just going to move on after that point. But what if I want to know, instead of even 1,000, 2,000, 3,000, what if I want to know how much is left after 2,700 years? All right? So let's do that again. We're still working with our 80. That's our parent. So we still have our daughter, which is our unknown. So you have your 80. This isn't going to change. 0.5. 2,700 divided by 1,000 in our exponent. We work our exponents first. So we're taking 0.5 or 1/2 to 2.7, the power of 2.7. That's our exponent. So when we raise that 0.5 to that 2.7, we get this number, 0.153893. And then we just multiply that by 80, and we get approximately, I'm just going to roughly round it, 12.34 of grams, we'll say, is left. Because remember here, so we've already gone through, at 2,700, we've already gone through 1 half-life, so 1,000, a second half-life, so we're in between our second and third half-life. And I've already calculated the second half-life for you, and if we calculate a third half-life just using 3,000, we'll get 10 left. So this is in between 10 and 20. So it's in between our second and third half-life, so this works. I just wanted to show you how this little equation you can solve for daughter elements as long as you have these are both known. There is a way to solve for this if these are not, if this is not known, but that has to deal with logs and stuff like that, and we're not going to get into that here. So as long as all of the stuff on this side of the equation is known, you can calculate a daughter roughly using any half-life you want and any amount of original material. So that's the only equation. I promise no more. Okay, so that's the basics of radioactive decay and half-lives and stuff like that, and that will work for any element, any amount of material with any half-life. But, like I said before, in the case of uranium lead, which is what I'm going to talk about, I don't care about carbon-14 because carbon-14 I don't deal with. Carbon-14. Now, this is where some of the disconnect comes. Carbon-14 is ingested by living things. That's why we all have it within us. And when we die, we stop intaking carbon-14 from the atmosphere or from the food we eat or whatever, okay? However we get that radioactive element into us. So we stop consuming it, and then the carbon-14 that's in our bodies decays as we do. In the half-life of, what is it? I don't know, 5,700 odd years, top of my head. So after 50,000 years, you can't use it to date anything. And you can only use it if you're dating carbon. Well, the rocks I deal with don't have carbon. Well, rarely do. We don't date that part. And they're a lot older than 50,000 years. So carbon-14 can't even do this, okay? And I think that's where some of the disconnect is, because creationists focus so much on carbon-14 that they don't realize there's a whole other thing. And when you're talking about uranium lead, you're not talking about a rock getting its uranium from the atmosphere, or this rock consuming something to get uranium, okay, once it's a rock. Rocks are not living systems. They don't eat, they don't breathe, okay? So how they get their uranium is completely different than how you and I ingest carbon-14. That's the big, huge disconnect, okay? And I've just explained that to you, so you can, it's not the same thing. Like I have this igneous rock here. This does not breathe, okay? This does not eat. Once it's in solid form, it is in its solid form until it either weathers into smaller particles or becomes heated through metamorphism and then eventually remelted. That's something that I need to stress over and over and over when it comes to young Earth creationism. Inanimate objects are not living systems. They don't function like us. That's why that whole argument about if I leave a bunch of parts laying around, they're never going to assemble into a 747 when talking about evolution. That's because the two aren't even remotely related, okay? So you cannot take organic concepts of living systems and apply them to things that do not act like living systems, okay? I'm done beating that horse. Uranium, lead, uranium, I'm not going to give you, there's a couple different isotopes. We're just going to use, I'm trying to keep this simple. Half-life of 4.5 billion years. G is billion. In geology, we usually use G. Okay, so if you see GA, that's what it means, billions of years. So 4.5, that's a huge amount of time. Well, the uranium on Earth was created in a supernova. We don't know where, we don't know when, we just know, obviously, after the universe was born, that a certain amount of uranium was created during a supernova of a star that would eventually, the gas and dust would reform our solar system. So, why isn't the uranium give us the age of that supernova? Or at least the age of the formation of the solar system? 4.5. Well, if something solidified at 4.5, then yes, it would. All right, but we don't get, if I take a rock like this granitic rock here, I take this here and I pull, we're going to talk about a couple things here. Zircons is one. All right, we're talking minerals because this is what we use to date, okay? So zircons, if I pulled some zircons from this and I dated them, and we'll get into correction methods here in a little bit, but I date those zircons, I am going to get the age of that rock, and we'll just say that rock is 1.8 billion years. This doesn't mean its accuracy limit, all right, of the testing. That's dependent on your equipment, the technology available at the time, and that is rant for another day. So I get the age of the rock. Well, why do I get the age of the rock and not the age of the solar system or the age of that supernova? Because of how minerals form from a melt. Okay, you can see I've written Baddeleyite up here as well, because these two elements, when we're going to talk about undeformed, unmetamorphosed igneous rocks here to get our uranium lead for right now. So we have our zircons and our Baddelytes. These are the two we date the most. And now zircons are real good for things like granites, intermediate rocks to felsic rocks. But eventually, if your magma is too saturated, what that means it has too much quartz in it, you can't even use zircons, all right? But the vast majority of things we like to date, like granitic rocks, they solidify in a nice temperature range where zircons will form, and they have coarse crystals, and coarse crystals are what you like to date because the bigger something is, the easier it is to work with in this case. And we use Baddeleyite for ultramafic rocks and more mafic rocks, like periddotites and lampreyfires, things like that. We use Baddelytes, and the reason why we use these different ones, I need to touch on real quick. I've actually done a whole video on this. I'm not going to beat it too much. Is Baddelytes will form at high temperatures like periddotites will, okay? So they are one of the first things to form that has to do with Bohn's reaction series, because as minerals form from a melt, well, we don't consider it a rock until it's in its solid final state after everything is crystallized, because there's gray areas. And Bohn's reaction series, Bohn and Tuttle, over the past 100 odd years, they figured this stuff out, that as certain minerals start to crystallize out of melts, some of them will exchange ions with that magma and become totally different minerals, as in the case of plagioclase to feldspar, and others will just change their form entirely, okay, as that magma body cools. So it's a function of chemistry and a function of temperature, and you will get certain minerals depending on that. Not all magmas are made of the same thing. It's not like you have a magma body, say this is the surface of your Earth in cross section, you get a, let's put a little house up here just so you know it's a cross section, okay? It's not like your magma comes up, and we'll just say, and I'm going to use the term melt instead of magma or lava because it can either be on the surface or under the ground. It doesn't matter, that's irrelevant. So this melt comes up and intrudes into the rock. As it does that, it's going to do some things. Even if it's chemistry, let's say the mantle where all these rocks come from are exactly homogeneous. They all have the same chemistry. That's still going to change as they come up, because as a melt comes through, if this rock is fractured, it's going to follow those fractures and not incorporate a lot of the country rock. But if there aren't any fractures or very little fractures, a lot of this country rock is going to get absorbed, and this could be sedimentary, igneous, or metamorphic. So it's going to add to the chemistry, okay? It's going to change the chemistry. And as this cools, certain minerals are going to form first in a specific order. Those will settle out if the chamber lasts long enough, in this case, this melt being underground, and new ones will form, but you'll get a sort of differentiation of minerals throughout the body of the melt, okay? So it's not like this thing intrudes and just crystallizes and you get a specific set of minerals. That does not happen, okay? So now that I've explained to you that every single igneous body on the planet is not homogeneous, and a couple of reasons why, and that's assuming the mantle is homogeneous, which it isn't. So anyway, so now I've explained that, and I've explained that certain minerals form in a certain order based off the chemistry, what's in the rock, what's available to make those minerals, and the temperature of that melt. And then, like I've talked before, I mean, typically that's a good typical temperature, high-end temperature of melt bodies of melt is about that. And we will get Baddeleytes formed, but these form at really high temperatures, extremely high, like ultramafic and mafic rocks will form like peridotites. So we don't really get Baddeleytes in things like granites, but zircons can be incorporated into peridotites and things like that as phenocryst, as foreign clasts. So that's why we date the Baddeleytes when we date ultramafic rocks, because we know those formed from the melt, okay? But we also have zircons, which we use, like I said, for granitic rocks. It's the most common that we date using uranium lead. And you can see the chemistry is different. As the magma body cools, certain elements get used up. Zircons are going to be the first things that form. Well, Steve, why am I talking zircons? I'm talking about uranium lead. And I'm about to get into that. Because sometimes these can be substituted for other elements, like uranium. Okay? Due to their chemistry and their bonds, they will often include uranium in their structure, okay? They do not, so you can get uranium as a substitution. We'll just use the Baddeleyite. Actually, let's get rid of Baddeleyite because I'm not going to talk about it again, okay? I've gotten rid of Baddeleyite because I've done a whole video on this. I'm not going to talk about it again. But you can substitute zircons for things like uranium. Okay, and that's what we date. We don't date the zirconium atoms. We date the uranium atoms inside. That will bond with the rest of this, and that's what we date. Well, does lead ever do it? No. See, the thing with lead, fortunately for us, it melts at a very low temperature. Okay, so it is going to be, even if it is present in a melt, in an igneous melt, it's not going to really want to bond with anything. It's going to eventually, and lead is very rare in any igneous body anyway because it's extremely heavy. It might be common near the outer core or something like that, but for the most part, it's not very common, okay, in melts. But even if it was, it's going to be the last thing to, because remember, things as that magma body cools, this isn't going to bond with anything until a magma body cools really low temperature. This temperature will drop and drop and drop, and basically anything below this is going to be a solid. There's not, when this crystal forms, this zircon forms, it will not have any lead in it, okay? So we'll say we have a zircon, we'll say we have a big zircon crystal. We'll say it weighs 1 kilogram. Okay, so we got a big one. And we'll say 1 gram of that has uranium in it. We are not going to see any lead in it if it has just formed. We date that, we are going to get a date of 0. That's why you do not get the age of the mantle or the age of the solar system or the age of the supernova, because nature discriminates against that daughter element in the case of uranium lead. You're not going to get leads substituting for zircons. You'll get uranium. And it doesn't matter. And has that chunk of uranium been decaying since the last supernova? Sure, it has. But that doesn't matter, because you're only going to have uranium forming as a substitution for zirconium in your zircons. You're not going to have any lead. So if we have a 1 kilogram zircon and 1 gram of that is uranium, and we run this, we're going to get an age of 0. It's going to continue to decay. So if we have that 1 kilogram, this is not what a zircon crystal looks like, but say we have that 1 kilogram crystal and we have 1 gram of radioactive uranium in there, okay, and we have 0 lead, we know this thing just formed. Well, what if we don't have 0 lead? Okay, what if we have 0.5 gram of uranium and 0.5 gram of lead? Well, we know that rock is this old. If we have 0.9 grams of uranium and 0.1 grams of lead, we're going to have something significantly younger than this. I'm not going to go through the maths with you, but because we're still within that first half-life. I mean, you can plug it into that equation that I gave you if you want, and you can figure it out. Okay, so to sum that part up really quickly, the reason why the age of a zircon gives us the age that the rock solidified from a melt is because of the chemistry of the rock. At the temperature, a mineral will form in a melt, and the fact that it will exclude lead because lead does not substitute for zirconium. Uranium will, but not lead. So if there's any lead in this zircon, it's from decaying. I'm going to talk about concordia plots or diagrams because this is our correction method. Now, can something happen to these zircons to give us a different date or a different set of dates? Yeah, it can. The zircon can be reincorporated in a low temperature melt and as a xenocrystal, and we can get an anomalously old age. But there are different things, metamorphism, it's things like that, can mess with the exact date. So this concordia diagram or plot is how that is corrected for. Now, you have your X and Y axes. I'm not going to get into, the details of this. I'm just going to show you basically how we compensate for it. If you want to know more about it, at the very end, after the credits, you'll have my references there. You can dive deeper into detail. Well, now what you're going to have on these X and Y axes are 2 different lead and uranium ratios, which I'm not going to talk about here because, like I said, there are different isotopes of uranium that will decay into different isotopes of lead. Okay, so you do a comparative there. All right, I'm not going to draw them there. Just understand that's what's there, and there's an idealized curve that these will follow, and that is slapped with time. Half-lives. 2.25. We'll just do 2. This is a rough. 2 billion, 4.5 billion, 1 billion, 0.5, etc. So we have this idealized graph based on our uranium-lead ratios. Now what's going to happen is as we date the rocks, ideally we should get a lot of stuff really close to this line. But that's not usually what happens. Usually what happens is you might get a cluster here because you had some, reincorporated into xenocrysts, and you might get, one here, and then you'll get, a couple over here. You get a big cluster right here, And what those will do, and this is very sloppy and I apologize, is, or you might even get some like up here or something like that. But what that'll do is that will create a line due with two intercepts. You're going to have two intercepts, okay, based on this. All right, this is your lower intercept. This plot based on this ideal curve eliminates this other, it kind of corrects for this stuff, okay? So your date here, based off the graph, looks to be about 1.1 GA. It will be your lower intercept. This is what we use to correct for an undeformed igneous rocks, or rocks we expect are undeformed, using zircons, like in a case of a granite. So we have compensation methods. Say we get something like this, all right? We don't really have a set intercept. We have one intercept we can use. There's a couple things that happen here. Now, in science, when you see something like this, you don't sit there and go, oh, my uranium lead dating techniques are totally invalid because I got a crap set of data. It's not what you do, because it's reliable in every, say this is the 13th rock you've dated, and out of the other 12 gave you nice intercepts, this one does something like this. You don't toss the baby out with the bathwater because of an anomaly. You sit there and say, one, how did I F this up? Okay? Did I screw up? Was my methodology wrong? Did I leave a step out? Is the equipment calibrated correctly? Whatever. Another thing is, we know, using other methods that I'm not going to talk about because this will get way too long, what could have happened is differentiated magma chambers, something like that, a long-lived magma, something like that, okay? And you know, I had it to 4.5 billion years. This could be 0.3 right here, and this could be 0.5. So even with something wacky like this, we know it's in that range, okay? So you just don't throw the whole concept out because of something like this. And this rarely happens, but occasionally it does. So you can't get focused on one dating method, because like I said, carbon-14 is an organic process. Radiocarbon dating is based on organic chemistry, and that, and you mean, this is physics, okay? This is physics. Radioactive decay is, in this case, would be geophysics, but based on the geochemistry of the rock. So the two are tightly intertwined. In carbon-14, you have biochemistry, you have organic chemistry, okay? These things, how you get those elements into the mineral or whatever you're trying to date is an important part of that process. So you can't get hung up on an organic dating method like carbon-14 when I'm talking about uranium lead. That doesn't make sense. We refine our concepts and theories. That's why science changes. That's why hypotheses get incorporated into larger theories, or they get discarded and we move on, because it's a process. All right, it's something. It's what we do for us to describe what we observe and can predict. It is not infallible. We as humans make errors. We do that all the time, and that's an important part of who we are, and that's how we learn. And I wish our failures were publicized as much as our successes, because we all love to celebrate our successes. Woohoo, I did good, look, I did this. But those successes are usually built on a pile of failures, and you learn from failure. So you change and adapt. The scientific method works really well. But like I keep saying, it's a process, okay, that we use. And it does eliminate biases to a degree. Yeah, we as humans, we have our eyes, our nose, our mouths, our hands, to observe the world. We can develop technologies to see things we can't, but even that's based on our how we are built. Okay, so there are some inherent biases there, but we can correct for those. And then there are societal biases, but those are actually the easiest to correct through the scientific method, because others can come and verify or falsify what we have done. And that is key in science. That is why, you can argue all day, all you want about anything. In the end, if you can't show it, you don't know it. Right? If you can't make a prediction about it, an accurate, precise prediction, not a prophecy, not some vague, obscure reference, but something specific, then you've got a good working hypothesis. Okay, but anyway, I think I'm going to wrap this up. I think I've rambled enough. I just hope that clears up why, when you date a rock, an undeformed igneous rock like a granitic rock, why you get the age of the rock when it's solidified from a melt and not the age of the supernova that the uranium formed in. But anyway, that's it. If you have any questions or comments, please leave them below, and I hope you learned something.